Linear regression is one of the simplest machine learning algorithms that helps us understand the direct relationship between two variables. Imagine we have two main characters in the story, our independent variable, like the cause, and our dependent variable, which is the effect. Now let's see how they connect. And here comes the magic. The line shows how one influences the other. Once you add the axes, now that we know that they're connected, let's put them onto a proper graph so that we can see the full picture. Here are x-axis for the independent variable and our y-axis for dependent variable. Each dot here represents an observation, an input value and its corresponding output value. What we want is a straight line that best represents the relationship between x and y. Mathematically, this line is represented as y equals beta naught plus beta 1 x, where beta naught is the intercept and beta 1 is the slope. The slope is simply rise over run. How much the line rises up or down for each step we move to the right. Sometimes slope is also called as weights. It is measured as change in the dependent variable over the change in the independent variable. If the slope is positive, the line goes upwards. As x increases, y also increases. If the slope is negative, the line goes downwards. As x increases, y decreases. If the slope is 0, the line is flat. X doesn't affect y at all. The bias is the point where our line touches the y-axis. It's the value of y when x equals 0. Change in bias shifts the position of the line up or down without changing its angle. If the bias is positive, line starts higher on the y-axis. If the bias is negative, line starts lower on the y-axis. The algorithm wants to describe our data with just one simple equation, that is y equals beta naught plus beta 1 x. But it doesn't know the right values of beta naught and beta 1 yet. So the model trying different slopes and intercepts, changing position and angle of the line again and again until the line finally settles into a position that best matches the overall trend of the data. That's the moment when we say the model has the best fit line. Now, if we look closely, not every data point lies exactly on the line. Some points are above and some points are below. The little vertical gaps between the actual points and the line are called as residuals. Each residual tells us how far off our line's prediction is from the actual value. Adding the error term in the equation represents those differences, the part our straight line couldn't explain perfectly. To note, the line explains most of the pattern, but not every single detail. Residuals can be considered as three types. Positive residual, the points that lie above the line. Zero residual, we could consider that line is a better fit. Then we have negative residual, the points lie below the line. In simple regression, we had just one feature on x axis and we fit a straight line in 2D. But what happens when we add more features? Each new feature adds another dimension. When the regression model uses two or more independent variables to predict one target variable, it is called as multiple regression. With two features, we are fitting a plane in 3D. With three features, we'd need 4D to draw it, and beyond that. It becomes impossible to visualize. So, in multiple regression, the number of features is directly proportional to the number of dimensions the model works in. Even if we can't picture all of it, the math is doing the same job, fitting the best hyperplane through the data. Here, y is the predicted output, p is the number of features, n is number of samples in your data set. All right, we have got this regression line, but here's a question. How exactly is this line formed from the data points? Remember, the line doesn't go through every point. Some points fall above the line, some fall below the line. The big idea is the line is formed by minimizing the residuals. But here's a problem. Some residuals are positive, some are negative. If we just add them up, the positives and negatives will cancel each other out, almost like they are hiding the real error. How do we measure the distance between the predicted values and the actual values? And that brings us to the idea of a loss function. To fix this, We square the residuals instead of just summing them up. Squaring makes every distance positive, so nothing cancels out. It also magnifies big errors, which means the line gets heavily punished for outliers. For mean square error, it's the average of all those squared distances. It's always differentiable, which means we can apply gradient descent to optimize it. The error surface only has one local minima, but MSE also has some drawbacks. It is sensitive to outliers. Because we squared the error, the unit of the error isn't the same as the target variable. So, how do we fix the outlier problem? That's where the mean absolute error comes in. Instead of squaring the errors, we take their absolute value. That way, an error is an error. It doesn't just get magnified just because it's big. Mean absolute error also has some advantages. It is in the same unit as the target variable. It's more robust to the outliers, but also has some drawbacks. The absolute value function is not differentiable at zero. It makes optimization harder, so we need to use subgradients that increases the complexity a little. Now, if about 10 to 15% of the data are outliers, then how do we tackle this situation? We need the best of both worlds, mean square error and mean absolute error. There comes Huber loss. For the majority of the data points, it behaves like mean square error, learning smoothly. For outliers, it switches to mean absolute error mode. Huber loss gives you a model that's both stable for most data and robust to unusual cases. Here, delta is the hyperparameter. This figures out whether the data point is an outlier or not. The Huber loss curve in green shows how it combines the best of both worlds. The blue line is the near zero error that looks quadratic. For large errors, it turns like MAE, avoids being pulled too hard by outliers. When outliers make up to 10 to 15% of your data, it adapts without letting them dominate. But are we done? Not really. Because once the model is trained, we need a way to evaluate how good it really is. That's where RMSE and R square come into the picture. Let's start with root mean square error. Remember, mean square error give us squared units, which made interpretation tricky. RMSE simply takes the square root of mean square error, bringing the error back to the same unit as the target value. Now, RMSE tells us the size of the errors, but what about the quality of the fit? That's where R square comes into picture. It is also called as coefficient of determination. If r square equals 1, it means that the line perfectly explains the data. If r square equals 0, that means the line is no better than just predicting the average every time. So far, we have been using mean square error to measure how well our line fits the data. The cool thing about MSE is that it's smooth and differentiable. And whenever something is differentiable, we can use calculus to find its minimum, the point where the error is the smallest. Here we try to adjust weight and bias, beta naught and beta 1 coefficients. We take the derivative of the loss function with respect to weights and bias. These derivatives tells us the slope, whether we should increase or decrease the values to reduce the error. Here alpha is the learning rate, W is the weight, and B as the bias. If your steps are too big, you might just overshoot the valley and bounce around. If your steps are too small, you lunge forward forever. With just the right step size, you steadily converge to the bottom. Here, learning rate determines the step size. So the algorithm does this. Start with a random weight and bias, compute predictions, calculate the error using mean square error, take derivatives with respect to weights and bias, update weights and bias using the learning rate, repeat until the cost function stops changing much. This loop is what allows the model to learn the best fit line step by step. When a model gets too complex, it stops learning real patterns and starts memorizing the data. In machine learning, this happens when the weights of the model becomes too large, leading a case called overfitting. Think of it like a student who memorizes every single question in a practice test, but then struggles with a new question in the exam. To fix this, we introduce a penalty term in the cost function. This penalty discourages the model from blowing up the weights, forcing it to stay simpler and generalize better. L1 regularization, also called as lasso regularization, with diamond penalty. With L1 regularization, the penalty is the sum of absolute values. Here, weights are not just reduced, they are driven all the way to zero. L2 regularization or ridge regularization uses circular penalty. With L2 regularization, the penalty is the sum of squares of the weight. This gently pushes all the weights to be small. Elastic net combines the best of both worlds of L1 and L2 regularizations. Elastic net penalty region looks like a rounded diamond. It's a combination of both circle and the diamond shape. We can conclude that L1 regularization uses norm 1, eliminates some features entirely, simplifies the model, reduces the dimensions. L2 regularization uses norm 2, reduces the influence of all the features and smoothens the model. ElasticNet combines L1 and L2 when feature distribution is unknown, when outliers could also add some value. Types of regression. Types of regression with continuous outcomes. First is simple linear regression. It models the relationship between one predictor and one continuous outcome. It's like predicting a person's weight based on their height. Next one is multiple regression. It models the relationship between two or more predictors, that is the features, and one continuous outcome. It's like predicting the house price using square footage, number of bedrooms, and neighbor rating, so on. Next is regularized regression. It adds a penalty term to the regression to reduce overfitting and shrink large coefficients. Fourth is interaction regression. It includes interaction terms like multiplying predictors to capture when the effect of one predictor depends on the other. Next is polynomial regression. It extends linear regression by adding powers of predictors like x square, x cube to model curves instead of just straight lines. Next is stepwise regression. It is an automated method that adds or removes predictors step by step based on their statistical contribution. Let's think of it like predicting the quality of a cake. Using simple regression, in simple regression, we use just sugar's effect to predict the quality of the cake. In multiple regression, we use sugar, flour, butter all together. In regularized regression, we only keep the most important ingredients and discard the extras. In interaction regression, sugar and butter together amplify the sweetness differently. The interaction is taken into account. Next is polynomial regression. It accounts for nonlinear patterns. Too much salt, again, makes it bad. Next is stepwise regression, testing which ingredients matter the most, keeping or removing step by step. Now, with categorical outcomes. These are used when your outcome variable isn't continuous but categorical, like yes or no, 0 or 1. First is binary logistic regression. It is used when the outcome has two categories yes, no, 0, 1, true, false. It's like predicting whether a customer is going to buy a product or not. Next is ordinal regression. It is used when the outcome has ordered categories where ranking matters. It's like prediction of the customer satisfaction. Next is multinomial logistic regression. It is used when the outcome has more than three categories without order. It's like predicting which mode of transport someone chooses, like car, bus, flight, train, whatever. Discriminant analysis, a classification method that finds linear or quadratic combinations of predictors that best separates category. It's like predicting whether an email is spam or not based on word frequency. Let's look at a big picture. With binary logistic, it's like a light switch. It can either be on or off. Ordinal logistic, it's like a ladder. Categories are steps in order. Multinomial regression is like choosing an ice cream flavor vanilla, chocolate, strawberry. There's no inherent ranking, just multiple choices. Discriminant analysis. It's like drawing boundaries on a map to separate different regions. Now let's look at some of the Properties and assumptions of linear regression. We assume that the relationship between the predictors and the response is linear in parameters. This doesn't mean that the data itself has to form a perfect straight line, but the model equation is linear in the coefficients. Second property, multicollinearity. It happens when two or more predictor variables in a regression model are highly linearly related. Multicollinearity is like having multiple friends telling you the same story, just in slightly different words. The story is clear, but who to credit becomes confusing. Third property is residuals should be uncorrelated with predictors. If residuals are correlated with predictors, the feature values, it means that the model hasn't captured all the information from the features. Fourth property, according to Gauss-Markov theorem, the estimator is linear in parameters, is unbiased, where expected values equals true parameters, has minimum variance among all the linear unbiased estimators. Fifth property is about the characteristics. It says linear regression is sensitive to outliers. A deterministic model gives the same exact output for the same input every time. A parametric model is one that summarizes data using fixed number of parameters within an assumed functional form. Supervised algorithm that learn from labeled data. Property 6, we expect residuals to be normally distributed with zero mean and constant variance. Each predictor contributes independently to the response.